Let's see, we were in 4, let's see, 5. So if we have our base set being the integers, then there's a relation, and Shai's going to get into these a little bit more when he starts talking about a little bit of number theory. So there's a relationship equivalence modulo 3. This means, so two numbers are equivalent modulo 3 if they have the same remainder when you divide them by 3. So So in this case, 1 and 2 would not be equivalent modulo 3. So this is not in equivalence modulo 3. But 1 and 4 would be, as would 9 and 333. Does everybody understand this relation?
Just in modulo form for the second example, would you write?
Yeah, so we could write this as 1 is equivalent to 2 mod 3. So that's another way to write this. Or I guess you could even say...
Oh, that's not.
Oh, right. So in this case, we could write 9 is equivalent to 333 mod 3. So those are just different notations. This is the more usual notation. This is not. So the last relation that I wanted to talk about was subset relation. So if A is a set of sets, let's say A is all the subsets of 1, 2, 3, then the subset relation is the relation that says this subset is a subset of this other subset. So, for example, 1 is a subset of 1, 3. And I guess the more usual way of writing this, we would say 1 is a subset of 1, 3. And 2 is not a subset of 1, 3.
But they're all subsets of A.
Exactly, and so we could say that this is really bad notation, actually. I shouldn't have even done this, but I just changed it to the normal subset notation. So, okay, so does everybody understand what a relation is? Teresa?
Why do you use the A cross A? Like, what is that cross supposed to mean?
So what the cross means is ordered pairs of elements of the set. And they're ordered exactly because we might have a case where A comma B is in the set, but B comma A is not. So
Is it in relation to any cross we've previously seen, or is this a new cross?
no, this is the same cross we've seen before.
Same. Okay.
Yep. So this cross is just ordered pairs A comma B, where A and B are in A.
Does that allow AA to be a possibility?
Yep. Yep. This allows AA. And sometimes it's easier, in fact, it's maybe usually easier to think of our relation in terms of these dots and arrows rather than in terms of these ordered pairs. I personally prefer the ordered pairs. In fact, Prolog uses relationships in exactly this way in terms of ordered pairs. And we talked about Prolog at the very beginning. I don't remember if anyone remembers. But essentially in Prolog, you can define relations. You can just say, okay, here are some relations, and here are the things that satisfy these relations. Go find my answer to this really hard, convoluted problem. And it just sort of recursively searches through all your relations and somehow magically finds the right thing at the end. So that's kind of cool. So
in number 6 up there, if A were just the set 1, 2, 3,
mm-hmm.
rather than all subsets of 1, 2, and 3,
Mm-hmm.
then 1 would still be in R, right? 1 would still be a subset of 1, 2, and 3.
So
Is that right? But 1, 3 would that be a subset of? I'm trying to figure out how this is different from just if A were 1, 2, and 3, rather than all subsets of 1, 2, and 3.
So if A, so Chris is asking if we have just the set A equals 1, 2, 3, right? Then in this case, we couldn't, well, so if we consider the sub is a subset of relation on this set, the only element of it, I mean, it doesn't really make sense because is of subset means that this must be a set, or this must be a set, or this must be a set. So if we think of those as sets, then we get into, yeah.
Because the relationship is by element.
Right. So the relationship, I mean, it doesn't make sense. I couldn't define a relationship on the set 1, 2, 3 is a sibling of, because it doesn't make sense to ask whether 2 is a sibling of 3 or not. So the relation has to make sense in your universe, whatever your universe is. And in this case, if we just have the set A equals 1, 2, 3, then is a subset of doesn't make sense on the universe of 1, 2, and 3. Unless you're a set theorist, but we won't go there. So, are there any other questions about relations?
What was something that wasn't a subset on that one?
2 was not a subset of 1, 3.
Oh, okay, but there's nothing that wouldn't be a subset of all subsets of 1, 2, 3.
Right.
Right. There's
Right.
nothing that has a 1.
Right. So this is not in the relation, but each of these is a subset of 1, 2, 3.
Is there some meaning to that little 6 by your R there, or 6?
No, it's just the sixth.
Okay.
Yeah.
Without the empty set, is that subset?
Yep, the empty set we could put, the empty set is a subset of everything. So the empty set, comma, 1, 3, that's certainly in our relation. Does that make sense so far? Okay, so people have already noticed some properties of subsets. So when we saw the parent relation, Bill was a parent of Michael, but Michael wasn't a parent of Bill. When we saw the sibling relationship, Andy was a sibling of Chris, and also Chris was a sibling of Andy. So that's one thing that that may or may not be true of our relation. R is symmetric if A comma B is in the relation, then so is B comma A. So if A is related to B, then B is also related to A. We'll say it's anti-symmetric if that's not true. So I guess I should be more careful if for every okay, so R is anti-symmetric if when A comma B is in R, B comma A is not in R. And this is when A is not equal to B.
For some AB?
For every AB. So this is if for every. And of course, it wouldn't make sense if A was equal to B, because then we would be saying if A comma A is in R, then A comma A is not in R. And so we just restrict ourselves to the case when A is different from B. Okay, so is symmetric. And the parent relation is anti-symmetric unless you're from West Virginia, and then we just don't want to know. Maybe you can delete that part. Okay. West Virginia. Yeah, even, I mean, I guess the parent. Yeah, I guess parent would be pretty hard to be not anti-symmetric, so we, yeah.
Unless you're from a bad time travel movie.
Right. Okay, so parent is anti-symmetric and sibling is symmetric. Less than or equal to, well, that's hard to say because, so, less than or equal to is neither one because, well, 5 is strictly less than 6, and 6 is not less than 5, but 5 is less than or equal to 5, and 5 is less than or equal to 5. So it's neither symmetric nor anti-symmetric. Well, maybe it is anti-symmetric. I said when A is not equal to B. Yeah, so less than or equal to is anti-symmetric. What about equivalence modulo 3? If 5 is equivalent to 2. Yeah, so equivalence modulo 3 is symmetric. Okay. Another property of relations. So a relation is reflexive if A comma A is in R for every A. Okay, so let's see. I guess equivalence modulo 3 is reflexive because a number has the same remainder as itself, modulo 3. So, yeah, and so is less than or equal to. So strict less than, that's not reflexive because A is not strictly less than itself. And let's see. Parent and sibling are both, well, I guess it depends on how you define sibling. If you define sibling to be, has the same parents as, then you're maybe, you have the same parents as yourself, so maybe you're a sibling of yourself. I guess that's a matter of personal taste. Should we call sibling reflexive or not? That's too bad. We'll see why in a minute, why we might want sibling to be reflexive. So this is by vote. What?
You could never say that you don't have any brothers or sisters if it was
That's true.
reflexive.
So let's see. Sibling is not reflexive, neither is parent. Again, unless you're in some bad time travel movie. So it is not. Okay. the last property that a relation might have, and this is maybe the most important, well, maybe not, I don't know which is the most important, is transitivity. Oops, I guess I'm on 4. So a relation R is transitive if, this is a little more complicated, so if A comma B and B comma C are in the relationship, then so is B comma C. A comma C. Good. Okay, so now there's a question. I guess you have to now be careful if we had C equal to A and our relationship was symmetric and transitive, then it would also have to be reflexive. So if a relation, well, before we do this, let's think about some other things. So let's see, less than is certainly transitive, because if A is less than B and B is less than C, then A is less than C. That's sort of how we define less than or equal to. That's not true. Yeah, if
That's true.
right. So yeah. So if A is a parent of B and B is a parent of C, that means A is the grandparent of C, not the parent of C. So parent is not transitive. Is it true for siblings? So you would think at first thought. So yeah, this now depends on how we define siblings. So if Andy's a brother of Chris, and Chris is a brother of Andy, that would imply that Andy's a brother of Andy. And so there's this question of
half brothers or half sisters.
Yeah, I guess we mean strict siblings. So sibling question mark. Because in this case we could have Andy Chris and Chris Andy. And this would imply Andy Andy. Yeah, I mean if in this case if we require that A is not equal to C, then it would be transitive. So transitive. Right, exactly. So maybe we should say if A is not equal to B is not equal to C, then sure, sibling is transitive. So that would make more sense. What else? I guess equivalence modulo 3 is transitive, because if 1 is equivalent to 4 and 4 is equivalent to 13, then 1 is also equivalent to 13. So these are basically relations. Are there any questions about relations so far? I've only talked about relations with one set to itself. You can also talk about, and I don't know if I wrote anything in the notes about this or not. You can talk about relations between two sets, and then well, okay, so if we had a set A and a set B, then a relation would be a subset of A cross B. And in this case, it's almost certainly easier to think of arrows from A to B. In this case, it's much easier to think of, here's A, Here's B. And here's a bunch of arrows. So this is just another way to represent our relation, and they're in fact the same thing because your ordered pairs are just the one thing here and the thing that it points to over here. So we can also compose relations. So if I have a relation from A to B and then a relation to C, like this, I now can think of the composed relation from A to C simply by first following an arrow from A to B and then following an arrow from A to C. So I'm actually really only going to want to think of these in terms of one relation to itself. So if R is a relation on A, then R squared is also a relation on A. It's the things A comma C, where A comma B and B comma C are in R. So what's the square of the parent relationship? We'd have to have A as a parent of B and B as a parent of C. So that'd be the grandparent relationship. Oh yeah, there was something else I wanted to talk about. I forgot to write this in the notes, so there's some relationships like parent that are not transitive. But transitive relations are somehow really nice, and non-transitive ones are kind of a pain. And so somehow it would be nice to take a relationship that wasn't transitive and find some other relation that contained that relation that was transitive. So we can talk about the transitive closure of a relationship. So the transitive closure of a relation is the smallest relation. I haven't talked about how one relation contains another. So one relation is compatible with another if in the first relation, well, in the bigger relation, if everything that was compatible in the first relation is still related or compatible in the second relation. So before I finish this definition, well, maybe I'll finish this and then clarify. So the transitive closure of a relation is a bigger relation that is transitive so let's call this one R, and the bigger relation TC of R that is transitive and contains all the relationships of R.
So for is a parent of, it would be something like is an ancestor of?
Yeah, something like that. Or is an ancestor and or descendant of. Maybe just as an ancestor of. Yeah.
Contains all the relationships.
So it contains all the relationships that were in your original set R. So what do I mean by this bit here? Well, I really just want to say R is contained in TC of R. And since these are subsets, that makes sense. What does that mean? Well, that means is if I have this new relation, and what I want is that everything that was related in the old relation is still related in the new relation. So, as Chris noted, the transitive closure of is a parent of is an ancestor of. Because a parent is certainly an ancestor of their child. It sounds a little weird. I mean, ancestors are supposed to be dead, but strictly a parent is an ancestor of a child, and so our original relations are respected. And furthermore, if Martha Washington is an ancestor of me, and God, who knows, the Queen of Spain is an ancestor of Martha Washington, then the Queen of Spain is also an ancestor of me. So it's transitive. Not that that's any of those are in the relationship, but that's okay. So does transitive closure make sense? Good.
How can you determine what the...
How can you determine it?
Smallest.
Yeah, so it's supposed to be the smallest bigger relation. What does that mean? Well, there's a couple ways to find it. So the first way to find it, well, we could just take our relation. So neither of these is computationally very useful, but I'm a mathematician, so I somehow want to at least have some way of computing these things. Okay, so the next thing I want to talk about is equivalence relations. And, well, it's unclear to me whether equivalence relations and partial orders are both really useful. And I don't know which is more useful. So, equivalence relations. Okay, so an equivalence relation is supposed to be one that's transitive and symmetric and reflexive. It's reflexive, symmetric, and transitive. So the idea is, it might be that, well, it depends how we define transitive. If we define transitive as I originally defined it with, then it's, yeah. So this may or may not be redundant if you, right. Yeah, maybe symmetric and transitive are complete, but we throw reflexive in there just to make ourselves happy. So, actually, actually, maybe it's not even redundant. Well, anyway. So the idea is that, well, we see equivalence. So this is somehow supposed to model equals. And these are somehow supposed to be the three most important properties of equals. I mean, certainly equals is reflexive because x is equal to x. It's certainly symmetric. If x is equal to y, then y is also equal to x. And it's also transitive. If x is equal to y and y is equal to z, then x is equal to z. So equals certainly satisfies these three properties. So that's good, since we've given it the name equivalence.
It's in the family of relationship one.
Yeah. Is in the family of, or is in the ancestral line of, or is in the lineage of. Is that what you mean? Something like that? Or
I don't know.
yeah.
That could also
There's some question of whether we can say this for any of our actual relationships. I guess if we define a person to be a sibling of his or herself, him or herself, then sibling would be. But so if we just say is in the family of, and we're not very specific, then we'll be fine. So what else? We erased all of our properties, and which examples satisfied them, of course. Another property that was satisfied was, or another relation that satisfied these was equivalence modulo 3. So equivalence modulo 3 was certainly reflexive, because if 1 was equivalent to 4, then 4 was also, 1 is equivalent to itself mod 3. Any number has the same remainder as itself modulo 3. It's symmetric, because if one number has the same remainder modulo 3 as another number, then that other number has the same remainder as the first number modulo 3. And it's transitive. So equivalence modulo 3 is one of these. And let's explore this guy a little more. So equivalence modulo 3, we're working over the integers, and so 0 was equivalent to 3, to 6, to 9, to 18, etc., and to minus 3, minus 6, etc. So this is the set of all things equivalent to 0. If we look at the set of all things equivalent to 1, well, we have 4, 7, 10, 19, minus 2, minus 5, dot, dot, dot. If I look at all the things equivalent to 2, I get this. Now if I look at all the things equivalent to 3, I'm going to land back up here again, because I'm going to get 3, 6, 9, etc. So this is kind of nice. In fact, I've divided up the integers into the ones that are equivalent to 0 mod 3, equivalent to 1 mod 3, and equivalent to 2 mod 3.
Well, why did you skip some numbers up there?
Pardon?
Why did you skip some numbers? It was 9, 12, 15.
Oops, I forgot. Oops. For no reason, just because I was not counting very well. See, this was supposed to be 12 was the next one. Yeah. Okay. So this is kind of nice. I mean, we have the equivalence class, if you will, of 0. And that, I mean, we sort of divided up the integers into 3 different sets. There's sort of 3 possibilities. Either it's divisible by 3, or it has a remainder of 1, or it has a remainder of 2. And that's all of them, and those are disjoint. If 5 appears in here, it doesn't appear up here. So it turns out we can do something like this in general when we have an equivalence relation. the equivalence class of an element of A. So if R is an equivalence relation, then the equivalence class of A is a set of all B such that B is equivalent to A in this relation. So A is going to be in the equivalence class itself because it's equivalent to itself, because an equivalence relation is reflexive. And, well, so this is all things equivalent to A. Does that make sense? So the theorem is, it turns out that the set of equivalence classes are a set of non-empty sets whose union is the entire set, and they're disjoint. The union of the equivalence classes is A, and the equivalence classes are disjoint. So certainly the union is in A because every element in A is supposed to have an equivalence class. So if we take the union over all of them, then we get all of A. They're disjoint, well, because if you have A in one equivalence class and B in another equivalence class that's different, well, they couldn't possibly be they couldn't possibly overlap because of this transitivity property. So let's prove this. Okay, so the union's sort of easy. It's sort of by definition. If we take the equivalence classes of all the elements, then of course we're going to get everything. The fact that if we have CA and CB different, then if CA intersected CB was not empty, so I want them to be disjoint. That means they have no elements in common. Suppose they do have an element in common. Suppose C is in both of them, little c. Well, it's in the first one if C comma A is in the first one. And it's in the second one if C comma B is in the relationship. So C comma A and C comma B are both in the relation. Furthermore, I know that the relation is symmetric. So C comma A being in the relation is the same as A comma C being in the relation. And now I have A comma C and C comma B in the relation. So this is by symmetry. And now I combine these two by transitivity to get that A comma B is in the relation. But that means that B must be in C sub A and A must be in C sub B, and therefore they must, they're equivalent, and so their equivalence classes are actually the same. So But we assumed at the beginning that C sub A and C sub B were different, so we've contradicted our assumption. I write a contradiction that way. I'm not exactly... The Hungarians write contradictions that way, and I studied math in Hungary, and so I don't know why they write them that way. Yeah, it's the same symbol that they have on all their, beware of electric things there, and so I don't know why they use it, but they do. So this completes the proof. Okay, so does that make sense? Are there any questions? I had 3 equivalence classes, and there's lots more nice math to say about that, but I won't go there because it could take years. So, so if anyone is interested in equivalence classes and that kind of things, I mean, they're useful in computer science because if things are equivalent, then it's much easier to deal with equivalence classes of sets than the big set you start with, maybe just, well, for whatever reason, then you sort of greatly reduce your problem to a much smaller one. They pop up all over the place in other math as well, and so that's sort of the idea. So these reduce problems to only studying equivalence classes. And that can be useful. This makes problems smaller.
So would like all the NP-complete problems be an equivalence class? Is that...
Yes. Yes. That one is reducible to the other in polynomial time. So there would be an equivalence class of problems. Okay. The last thing I wanted to talk about today was partial orders. So and I'm probably leaving something out, and I'll remember it, and I'll tell you tomorrow, because I always do. Okay, so now we're moving on to partial orders. And what's a partial order? So a partial order is another kind of relation, rather. So a partial order So it's a relation that is antisymmetric and transitive. So one of the examples we had earlier was is less than or equal to, or strictly less than, I guess, if we want to be careful. So less than is a partial order. I mean, in fact, less than is a total order. Every two. So a partial order, I don't want to go here. It's actually a total order, and if you want to know about that, come ask me later. So less than is a partial order simply because, well, if A is less than B, then B is not less than A, it's greater than A. And so it's antisymmetric. And it's transitive because if A is less than B and B is less than C, then A is also less than C. So it satisfies both these properties, so it's a partial order. Another partial order is subset of. So if we let A be subsets of 1, 2, 3, then subset or equal to is also a partial order on this set.
Doesn't have to be a proper subset.
Yeah, there's this whole question about whether or not it should be proper subset or not. And I'm going to say mathematicians are really bad. I mean, they always use this notation when they really mean this, and let's just use that. I guess antisymmetric doesn't say anything about whether or not something's reflexive. Because antisymmetric, remember, meant that if A comma B was in the set, then B comma A was not. And this was for A not equal to B. So if we leave the equal sign there, then it's okay. Because certainly a set is a subset of itself, but then the antisymmetry law doesn't come into effect because A is equal to A. Little a. Okay. So those are the examples we've seen so far that are partial orders. There's another example that I'll talk about in a minute. But first I want to talk about Hasse diagrams. So Hasse diagrams are ways of drawing our partial ordered sets. I guess a partially ordered set, oops, I should have written that down. So a partially ordered set, or a poset, is a set with a partial ordering. Okay, so the way that I draw a partially ordered set is I represent each element by a vertex or a dot, and I represent the relations by lines between them. But my lines sort of always go in one direction because it's antisymmetric, and so if I have a line one direction, then I don't have a line in the other direction. But what I'm actually going to do is not include all the transitive relations. So I can write down all my subsets of 1, 2, 3. Like this. And then, well, 1 is a subset of 1, 2 and of 1, 3. And it's also a subset of 1, 2, 3, but that is sort of implied by the fact that it's a subset of this and this is a subset of that. So I don't include all of the lines, I just include sort of the minimal ones to make this complete.
Now which ones would be the transitive lines?
So the transitive lines would be things like this, 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 and this. And so I could draw all those in, but those extra red lines are implied by the white lines that are there already, or the ivory lines that are there already. And so there's no reason to, well, yeah, I mean, if we wanted to be particularly complete, we could include them. But in fact, the ivory lines are enough because we know the other lines must be there by transitivity. So So the nice thing about this particular example is if you look at it at the right angle, it looks like the hypercube. And in fact, if you can get a picture of the hypercube of any dimension simply by taking the subsets of an n-element set. Because as we know, so the hypercube is supposed to have vertices corresponding to binary strings, and those are supposed to be in one-to-one correspondence with subsets of a set, of an n-element set. And so at least they're going to have the same number of vertices, and it turns out that the way we draw these Hasse diagrams, the edges also agree. So, let's see. There's a lot to say about partially ordered sets. I, in fact, in college took a whole class on them, so I'm obviously not going to tell you everything there is to know about them. But the question is how much to tell you.
Can you tell us where they get the name from? I mean, the equivalence ones, the name makes sense because it's equivalence and it's a relationship.
Right, so where they come from.
What's partial about it, and how are they ordered?
Okay, so that now comes back to why. So Doug's asking, why are they called partial orderings? It sort of made sense to call the equivalence relations because they were similar to equals. But this, what's a partial? Well, why do we call it partial ordering? So that sort of goes back to what it means to be a total order. A total order ordering on a set is anti-symmetric and transitive. And for every pair of elements A and B, either AB is in your set or BA is in your set. So, in your relation rather. So either A
Exclusive order?
Yes. I guess it is because we already assumed anti-symmetric. And so an example of a total ordering is less than, because each pair of numbers are comparable. We can say this one is less than this one, 5 is less than 6, or 3 is less than 5. So this is a total ordering. Because every pair of numbers is comparable. This is a partial ordering. So a partial ordering, we sort of lose the fact that every pair has to be comparable. Over here, let's see, we have 1 and 2, 3. And in this case, 1 and 2, 3, we can't compare them. 1's not a subset of 2, 3, and 2, 3 is not a subset of 1. And so in a partial ordering, we may or may not be able to compare every pair of elements. So that's where partial comes from. Brian?
Can you give us sort of a more real world and less math oriented idea of what a partial order might be? I mean, is there
An example? Yes, there is. Okay, so here's another real world example of a partial ordering. This dates back to World War II, and this was in fact when partial orderings were sort of first studied mathematically, and this is why. A lot of funding for combinatorics to study partial orderings comes from the Office of Naval Research, which seems sort of weird, but consider the following problem. So suppose you have a whole bunch of routes that need to be covered by airplanes. You have to get cargo. You're trying to get missiles or food or whatever. You're trying to get it from island to island to island. Say you have 5 islands. And each flight takes a certain amount of time. And, well, this isn't a very good way to draw the problem. Okay, so suppose you have a certain schedule of flights. So how should I best draw this? Maybe this way. From Hawaii to God knows where, somewhere else in the Pacific. And But at 4, we have to send another flight to somewhere else. And let's see. So we have sort of all these intervals of time that have to be covered by a flight. So the question is, how many, well, I mean, of course, our actual order would be much more complicated than this because we'd have so we'd have something like this, and we can order these intervals. So this is called an interval order. We can order 2 intervals if one's strictly less than the other. So we get a point for each interval. So here's our lowest one. And then this was, well, there were 2 more that overlapped it, and so they aren't lower than it. Or they aren't higher than it. Let's call these 1, 2, 3.
What are we solving for?
So the question is, how many planes do we need to cover all these routes? And I guess, first of all, there's the question of, well, if this one's less than this one, is there, is it possible to get a plane from here to here in time to cover that route? But that's going to make our life even more complicated. So let's assume that all the planes end up and start in the right place. Okay, so 6 and 7.
6 twice.
Oh, that's bad. Okay, so here I have 1, 2, and 3. And none of them are comparable because you can't use a plane to cover both 1 and 2, or both 1 and 3, or both 2 and 3 because they overlap each other. So 1, however, is strictly less than 4. And it's strictly less than 6, 7, 5, and 8, and we're not going to worry about that for right now. Okay, so 2 and 3, well, they're not less than 4. So we could put 2 and 3 up there, but that's okay. Let's see, so this is awfully complicated. Let's erase a couple. Yeah, right. I mean, so destroying some flights. So 1, 2, 3, 4, 5. Let's see, 1 is less than 4. 1's also less than 5. And 4 and 5 are not comparable. 2, I guess, is less than 5 also. And is that it? I think those might be all the strict less thans, because everything else overlaps. In any event, so the question is how many, well, first of all, is it clear how I got from my intervals to my partial ordering? So my partial ordering is, yeah, these are supposed to all go up. Namely, this order is supposed to be less than this one, or this interval is supposed to be before this one. So okay, so the interval I is less than the interval j if the interval I is completely to the left of the interval j. And so we can get all kinds of partial orders, all kinds of Hasse diagrams for these. So suppose we had something like that, and then the question is how many planes do we need to cover this, to cover all these routes? And well, first of all, which partial orders can even arise as interval orders? That question is maybe easier to answer. But the question is, so how many planes do we need? And so that's basically just a question about partial orders. The idea is we could use, because this interval is completely to the left of this one, we could use one plane for these 3 flights. We could probably use one plane for this, and then we'd have to use one plane for this, and a last plane for this. So the answer in this case would be 4. Question is, if you have some really huge partial ordering, I mean, it's obviously much more complicated than this to move your troops and your food and your missiles and everything else around in the case of a war. I really hate to use this example because I really don't like to say that I work for the government or the NSA or anything like that. But in any event, some mathematicians do, maybe I should say. In any event, the answer is, for a bigger, for some really big poset, we can still fairly quickly determine how many planes we need. And you can't just quickly glance at your poset, but it turns out the number of planes we need is equal to the biggest number, the biggest size of an anti-chain. I haven't told you what an anti-chain is, of course, but that's okay. So it's the size of a biggest anti-chain. An anti-chain is a set of elements that are all not comparable to each other. So an anti-chain in this case would be this guy, this guy, this guy, and this guy. So no pair of the sets in an anti-chain can be compared to the other. They all overlap. And so, of course, it makes sense intuitively that the maximal number of overlaps that we have is going to, that's going to give us a lower bound on the number of planes we need, because if there's 5 routes that overlap, then obviously we need 5 different planes to be flying each of those routes simultaneously. You have some work to do to prove that that's enough planes, but you can do it. So that's kind of cool. Where are we on time? Maybe not enough time to start something new. Are there any questions about what we've done so far today?
Which one? Why isn't there a box at the top green one?
Oh, I could have put a box there, but I can't put a box on both of them because then these two would be comparable.
Oh, I see.
So an anti-chain is the number, is a set of incomparable elements. It turns out, the other theorem that we need here is that the size of an anti-chain, the size of a maximal anti-chain, is also the number of chains that we need to cover our graph. A chain is something that's just dunk, 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 goes straight up. And so here we have 1 chain, 2 chains, 3 chains, 4 chains. And so the size, number of elements in maximal anti-chain is the number of chains we need to cover our poset. And I'm certainly, you can prove that. That's kind of a pain to prove, but it's not terribly hard. So, and it's certainly not obvious. So, are there any other questions?
Covering a poset, you're covering the vertices.
You want to cover all the vertices, yeah.
But there's a diagonal edge you can't cover.
Right.
Can't.
Right. We want to cover the vertices because those are the intervals that we need to, I mean, those are the planes that need to be, or the routes that need to be serviced. So I guess this question is also relevant in modern days to airlines when they have, 8 million flights they want to not cancel, and they sort of want to minimize the number of planes that they actually have to use, so they would probably use some algorithm to find the maximal anti-chain in order to figure out how many planes they needed and blah, blah, blah. So it's probably much more complicated because they also have to take into account that, the cities, the ending cities have to be close to each other or the same, and I wouldn't even want to think about the scheduling problems. But in any event, this kind of scheduling problem comes up a lot when you're looking at post sets, or post sets come up a lot when you're looking at scheduling problems. So.